All right, there's one last thing for us to look at here in Chapter 10, and that is the effect of temperature on the equilibrium constant. This is going to connect to some concepts that you learned back in Chapter 6 in the equilibrium chapter. And at the time, we kind of took some of those concepts for granted and didn't really go into a lot of detail as to why these things were what they were. But in this section, we're going to be able to get a better and deeper understanding. As a little bit of a review, we're going to think about this reaction, N2 plus 3H2 at equilibrium with NH3. This reaction is exothermic because I've shown that heat is on the right-hand side of the equation, so the reaction is releasing heat. Let's think about what would happen if you were to increase temperature. Think about whether that's going to cause the reaction to shift right or left, or if it's going to shift at all, and what that will do to the value of K. Go ahead and put in your answer. So hopefully you remember from the equilibrium chapter when we talked about Le Chatelier's principle that increasing the temperature puts a stress on this system. And so increasing temperature is like having more, heat. And when you put a stress on the system, Le Chatelier's principle says that it will react in a way to counteract that. So if you increase temperature, you're going to have to shift away from the heat. You're going to shift the reaction to the left. The reaction is going to now favor reactants more heavily. All right, so that helps us to figure out that the reaction shifts to the left. So now we have to decide between C and D. Does the value of K decrease or does the value of K stay the same? Now, K is the equilibrium constant, and so that word constant kind of implies that the value of K is completely unchanging. But I will remind you that there is exactly one and only one way that you can change the value of K, and it is by changing temperature. Because we have changed temperature, we will change the value of K. As the reaction shifts to the left, the position of equilibrium lies more heavily on the reactant side of the equation, and so that means that the value of K should decrease. Therefore, we say the reaction shifts to the left and K decreases here. Now, so far, all of this has just been a review of things that you previously saw in the equilibrium chapter. And as I said before, we kind of took a lot of these concepts for granted and just said, this is what happens without much of an explanation for the why behind it, I guess. And now let's see why changing temperature would be the only way that you can change the value of K. To see that, what we can do is look at the following equation that shows the relationship between K and T. It says the natural log of K is equal to negative delta H standard over R times 1 over T plus delta S standard over R. And so what we see here is an equation that relates these two variables, and it shows you that K is a function of temperature. Now, because the values of delta H and delta S for a particular chemical reaction are constant, if T is also constant, then K would have to be constant. T is the only variable that we would have in this equation. For the purposes of this class, we assume that delta H and delta S are like totally constant for a chemical reaction. It's not exactly true. Delta H and delta S are also functions of temperature, but very weakly so. And to see that, you have to do calculus, so that is beyond the scope of this class. Now, if you want to see where this equation came from, you could take a look at section 11 of chapter 10 to see a proof and a derivation of the equation. It's kind of a nice proof to look at to show how you can connect equilibrium to delta H and delta S. Now, you can do further manipulations of this equation to come up with something called the Van Hoff equation. And the Van Hoff equation allows you to calculate K at any temperature as long as you know K at some initial temperature and the value of delta H standard for the reaction. It allows you to convert K from one temperature to a new temperature. This equation takes the form ln of K2 over K1 is equal to negative delta H standard over R times the quantity 1 over T2 minus 1 over T1. In this equation, K2 represents the equilibrium constant at the new temperature, and K1 represents the equilibrium constant at the initial temperature. If you want to see a derivation of this equation or a proof of where it all comes from, I'll refer you again to section 11 of chapter 10, which goes through where this equation comes from. I'm not going to go through the proof here in these slides, because I'm not going to test you on that. You're being tested on being able to use these equations, and so that's what we're going to be talking about here in these videos. So again, this equation will allow you to convert K at one temperature to K at a new temperature. Now let's look at an example. So here we're dealing with the reaction S plus O2 as at equilibrium with SO2. and we're told the value of delta H standard is negative 297 kilojoules. And I'll remind you that when it's for a reaction, we imply that that is per mole of reactions. And we're also told that the Kp for this reaction at 25 degrees C is 4.2 times 10 to the 20th. We need to calculate the value of Kp at a new temperature of 85 degrees C. Now, in this problem, we have like a lot of stuff going on here. So one thing that's helpful for us to do is to begin the problem by thinking about what equation we're going to use. We're trying to relate K at one temperature to K at a new temperature, and the only equation that you have that deals with two Ks at two different temperatures is this ln of K2 equals negative delta H standard over R times 1 over T2 minus 1 over T1. This is the equation you're going to need to use in order to solve the problem. But there are so many variables and there's so much going on here. And so it's really helpful, I think, to take a moment to organize the information that you've been given. Right? So not just to organize the information, but also to define the variables. That's going to help ensure that you're plugging all of the variables into the right places in this equation, and it's going to help to ensure that you're solving for the right variable and that you're doing everything correctly here. It's so easy to make mistakes plugging things into the wrong places or solving for the wrong thing. So by taking just a moment to organize the information, this will really help to ensure that you're going to get a reasonable answer here. So what we have here is some initial temperature of 25 degrees C, or that's 298 Kelvin, and the equilibrium constant that's associated with that initial temperature is 4.2 times 10 to the 20th. Then we have a new temperature of 85 degrees C, so I'll call that T2, or that is in Kelvin 358 K, and the equilibrium constant at the new temperature is unknown. That's what the problem is asking for us to solve. This helps us to, again, organize the information and define all of our variables. One thing that I'll tell you here is that it doesn't matter how you index as long as you're consistent. So you could have also said that T2 is 298 Kelvin and K2 is 4.2 times 10 to the 20th, and then T1 would be 358 Kelvin and K1 would be the question mark. You could say that also, and you'd also get the right answer. You just have to be consistent with the indexing. You have to make sure that you put 298K with the equilibrium constant with that temperature, right? 4.2 times 10 to the 20th. You have to put 358K with the question mark, because that was the unknown. Now we recognize that to get to the answer to this problem, you're going to have to solve for K2. So we're going to go over to the next slide and do that. I'll tell you that the first step in doing that is going to be we have to get K2 out of the natural log. So we'll begin by taking e to both sides of the equation. So with the left-hand side of the equation, e to the natural log, those two operations wipe out. You're left with K2 over K1 equals e to the minus delta H standard over R times 1 over T2 minus 1 over T1. And lastly, to solve for K2, you can multiply both sides by K1. So K2 equals K1, e to the minus delta H standard over R, 1 over T2 minus 1 over T1. Now you can again start to see why it's so important to be labeling all of your variables so that you're plugging the right things into the right places, because there's a lot of ways that things can go wrong here. Because we took a moment to organize the information, we can say that K2 is equal to the initial equilibrium constant, which we defined to be 4.2 times 10 to the 20th, times e to the negative delta H standard. I'll remind you, delta H standard was negative 297 kilojoules per mole, so we'll plug that in. Negative 297 kilojoules per mole. Over R, we should use 8.314 here, and that's joules per mole per Kelvin. We've got to make the units compatible, so I'll turn the joules into kilojoules. I'll just divide that by 1,000. Times 1 over T2, which we define to be 358 Kelvin, minus 1 over T1, which we define to be 298 Kelvin. All right. This equation is a mess. There's a lot of numbers here, right? And so it's important for you to practice with plugging something like this into your calculator so that you know how many parentheses you need to use in order to get yourself to the right answer here. But first, let's take a look at the units. So the joules cancel the joules. This gets you to kilojoules on the bottom, right? That cancels the kilojoules on the top. You have per mole, canceling per mole from R. And then you have 1 over Kelvin here from the temperatures, and that cancels the 1 over Kelvin in R. So totally unitless, which is exactly what you want for an equilibrium constant. Now, when you plug all of this into your calculator, you'll find that the new value of K at 85C is 7.9 times 10 to the 11. And there's our answer. Now, it's helpful to consider whether or not your answer is reasonable. And let's talk about how you can think through that in this problem. We're going to take a look back at the reaction. When we look at the reaction, we see that the value of delta H is negative, meaning that the reaction is exothermic. So we can write that heat appears on the right-hand side of the equation. In this problem, we're raising temperature as we go from 25 C to 85 degrees C. If you increase temperature, we've previously talked about how that will cause an exothermic reaction to shift to the left, and that will cause the value of K to decrease. Is that what we observed here? We went from an initial K value of 4.2 times 10 to the 20th to, when we raised the temperature, it decreased to 7.9 times 10 to the minus 11. This is 100% consistent with the predictions that we learned how to make all the way back at the beginning of the quarter in chapter 6. So yes, this is totally reasonable. We have an exothermic reaction. Increasing T should cause the value of K to decrease, and that's exactly what we observed. If you had done this calculation and you found that the value of K was greater than 4.2 times 10 to the 20th, that would be an answer that wouldn't make sense. That would indicate that somewhere along the way you made a mistake, probably involving a sign convention, and so you should go back and check your work. Now, we can think of other cases and other examples. If we had an endothermic reaction and you increased temperature, then you would expect that the final K value should be higher than the initial, and that would be what you would predict as a reasonable answer, right? So it's helpful to think about different scenarios, different cases, and different situations, and also how to predict whether or not your answer is reasonable. There are a lot of ways that mistakes can be made in this problem, and by thinking about what a reasonable answer is, this helps you to check to see if you've made one of those mistakes, and you know, you can catch common errors that way. And that brings us to the end of chapter 10. So at the end of every chapter, as you know, there's the list of topics that we discussed that you can use as a study guide. There's actually a lot that we did in this chapter. Chapter 10 is a pretty long one. So we've got 1, 2, 3 slides worth of topics that we discussed here in chapter 10. And, you could look these over. They're posted on Gaucho Space, and you can see what we discussed here and use this as a study guide. Next up, we're going to do chapter 11, which is electrochemistry. This is going to be a really interesting application of what you've learned throughout the thermochemistry portions of this course. And you're going to use that towards solving problems that deal with redox reactions.